endocrine system, okay, with the endocrine system, it works very closely with the nervous system. So what is the job of the nervous system in general, everyone? If you could sum it up in just one word, what would it be? Communication. There we go. Communication, control, regulation. Okay, what were you going to say?
Pain.
Pain. Hopefully not so painful.
Yeah.
Okay. Hopefully not so painful. The endocrine system, they work very closely with the nervous system, and this is the way that we can maintain homeostasis. So basically how the nervous system works, from what you remember, you have some kind of a stimulus. Somebody's going to pick up on that stimulus. That stimulus, the information about stimulus is going to go to some centralized place where it's going to be integrated and interpreted. Then what will happen is there's going to be some kind of a response, okay, to that stimulus, all right? And it's usually going to be an undoing of something else. Similarly, the endocrine system will work like that. If we are maintaining homeostasis, we try to keep all of the levels of our ions, of our glucose, of our nutrients within a very defined normal range at all times. The reason why we have an endocrine system, one of the reasons why we have an endocrine system is that if we don't keep those characteristics within a certain range, and it falls out of that range this way, or falls out of the range here, we need to have mechanisms to be able to put that characteristic within its range. That's what the endocrine system is going to do. So we're going to talk a lot about what's called negative feedback and the function of negative feedback. It operates by negative feedback. And all it is just, this came from like a business slide. It's all about communication. Somebody is going to come up with the message. Who's the one that's going to come up with the message? It's the gland that's going to secrete a hormone. What is the message? A hormone. That hormone, that message needs to be sent to a recipient. How is it sent? Through the bloodstream. By definition, that is what a hormone is. It has to travel through the bloodstream. Whether it's going a long distance or if it's going a short distance. It travels through the bloodstream, it's a hormone. And there has to be a recipient at the other end. Somebody at the end that has to interpret what that message is and turn that message into some kind of purposeful action. What is the interpreter, the recipient at the end? We're going to call that, folks, the target cell. So you have a gland secreting a hormone, that's our message. That hormone is going to be sent through the bloodstream. It's going to reach a recipient called the target cell, and the target cell is going to end up responding to that hormone and providing feedback. This message will continually be sent until whatever goal we need to achieve at the end is achieved. The moment we reach that goal, we do not need to send the hormone anymore. So what is that goal? We're trying to get within that certain defined range. Once we're in that range, there is no need for the hormone to be secreted. Does that make sense? Okay, we're going to go more into it. All right. If you are curious what these are kind of playing Riddle Rush. These are two adrenal glands playing on the swing. Get it? Adrenal gland, adrenaline?
Get it.
Okay. All right. So in order for us to get to the endocrine glands and the hormones and what they are, we have to contrast them with something we may already know, which is called an exocrine gland. What's an example of an exocrine gland? Let's see if we can kind of remember. Give me an example of an exocrine gland. Let's go back to integumentary system, shall we? Give me an example of an exocrine gland. Sebaceous. Give me another example of an exocrine gland. The sweat glands. Okay. What do we notice about that? When you sweat, when you produce oil, does any of that go through the bloodstream? Mm-mm. Does that chemically change the skin cells that are going to be in contact with it? Or does it simply just coat them? Does it actually chemically change those cells? No. By definition, that's what an exocrine gland does. Versus an endocrine gland. An endocrine gland is going to secrete a hormone into the bloodstream, and that is going to chemically change or do something significant to the target, whatever that will be. And that target, in order for that target to be physiologically changed, it needs to have a receptor for that hormone. We don't have sweat receptors. We don't have saliva receptors. We definitely don't have oil receptors. We don't. That's the difference. So we'll talk about that. How the hormones are also classified chemically if we have time, and then mechanisms that will control hormone secretion, including negative feedback, okay? All right, so let's look at exocrine versus endocrine again. Let's fill in some blanks, okay? Secretes hormones into the blank. If it's an endocrine gland, where are we secreting hormones into, everybody? Into the bloodstream, very cool. These are what we also call the ductless glands. And these will stimulate responses in distant target organs because of the hormones actually having to travel through the bloodstream. And not just stimulate responses, this is what I mean by physiologic change. You can also kind of put there in parentheses, physiologically change the target. That's okay too. But that is, by definition, what is endocrine versus exocrine. Now let's look at exocrine. We're gonna secrete products onto the surface of epithelium, typically using what's called a duct. We don't need to use a duct all the time. Many times we do. If you imagine your cross-section of your sebaceous gland or your sudoriferous gland, you'll notice that cross-section. It's a lot of surfaces that are in there. So surface epithelium, that is what this is relating to. The target ends up being in direct contact, and also we don't actually physiologically change the target. Okay, so that's the difference between endocrine and exocrine. That's super, super important. Yes?
Would the ABO type 2 cell be exocrine line or endocrine? I'm just thinking about that.
By definition, that's a great question. So he's asking, would a type 2 cell that secretes surfactant, would that be considered exocrine? Because it secretes onto a surface, it would.
Okay.
It would, yes.
Yeah, I
Okay?
was thinking about that real quick.
Yeah, that's considered exocrine secretion. It's onto a surface.
Okay.
Right? It may not be, the cells may be kind of scattered, but that is still onto a surface, yes.
So the exocrine, are they glands as well?
They are glands,
So they're
correct.
exocrine glands, so they're in more or less direct contact with the target organ?
Yes,
Okay.
but it doesn't actually change the organ. And that organ is going to be some kind of an epithelial surface. Okay, for exocrine. When it's endocrine, the hormones have to travel through the bloodstream. They're produced by endocrine glands. It leaves the endocrine gland, goes into the bloodstream, travels through the bloodstream, and finds a target organ typically further away. So that means it has to leave the bloodstream and actually bind to a receptor at that end. Exocrine glands do not have receptors. Endocrine glands do. Okay? So, as these chemical messengers are going through the bloodstream, okay, we were gonna work by what's called hormones. So when you see hormones, you should be thinking endocrine right away, and they will signal responses, physiologically change that target. What kind of changes are we looking for, and why do we have the endocrine system? This allows us for us to maintain homeostasis, which is being within normal limits in a way, okay, and growth, metabolism, stress defenses, blood chemistry. There's a whole lot of effects that are endocrine effects that are mediated by the endocrine system. They tend to work very closely with the nervous system. We may even have certain hormones that are nervous system derived. We call those neurohormones, where they are produced as if they are neurotransmitters, but because they travel through the bloodstream, that's what makes them hormones. So we'll go over a couple of those. Hormones are also fairly slow acting. Slow acting versus your neurotransmitters. Neurotransmitters, it's an immediate effect typically. With our hormones, they can be slow acting, slow in terms of hours, slow maybe even in terms of years and days, okay? So slow acting, and this helps to integrate other systems. It can integrate with other systems. So, give you an example. There are certain hormones that are simply going to be for digestion. Digestive system, yes. Are they hormones? Yes. So endocrine is includes several other systems with the endocrine system, okay? So let's highlight nervous versus endocrine. Both, of course, are for communication. That's an important thing. But the differences are in the following: the chemical messenger, the location of the target, and how long it takes, the response time. Let's compare them. What is the name of the chemical messenger of the neuron? In general, the name of the chemical messenger of the neuron is called the name of the chemical messenger. What does the neuron send out and release to affect the next one? Neurotransmitters. Okay? What's the chemical messenger again of the endocrine gland? It's a chemical messenger, starts with an H, everybody? Hormone, very good. Okay, so we've got our neurotransmitter. This is released by this releases neurotransmitter. This one releases hormones. Location of the target. Location of the target. Your choices are nearby or far away. Nervous system, nearby or far away? Nearby. Where the moment the neurotransmitter is released, doesn't have to travel much, the target is already there. Endocrine system, nearby or far away? Mostly what? Far away. Response time, slow or fast? What do you think with this one, because we're so close to that target? Fast. And then this one is going to be slower. Very good. We're going to direct our focus just to the hormone part. And we have two types. There are two major classes of hormones based on the chemical structure. You're either protein-based or you're steroid-based. That's basically it. If you're protein-based, we can kind of classify you also as amino acid-based. So the reason why we call this general group of amino acids is that they can be individual amino acids as a hormone. They can be short proteins or peptides as a hormone, or they can be big proteins. So in order to understand this, you have to understand your main macromolecules. That there's differences between proteins and there's differences between proteins and steroids and the way they work. Proteins, for the most part, are hydrophilic. Hydrophilic. This ultimately depends on the type of amino acids that make up that protein, but we're going to classify them in general as more hydrophilic. Your steroid hormones, on the other side, on the other hand, steroids come from cholesterol. So this is one of the reasons why we have to have a healthy amount of cholesterol. They form the precursor for all of our steroid hormones. Your steroid hormones will also tend to have these word endings. Anything that ends in O or O-N-E will tend to be, I'm going to trash can, there's no trash can there. It's like all the way over there. I need to remind myself to throw this away. I'm going to leave this right there. Okay. Is what?
Say code to you.
I don't think I can code here. I'm horrible at that. I have no way. They tend to have O-L or O-N-E at the end. So even now you may be able to name some steroid hormones off the bat. Name me some steroid hormones based on that. Testosterone. What else? Progesterone. How about the stress one? Cortisol. Okay. What about the anti-itch cream? Cortisone. What is that? It's a derivative of that. All of those are steroid based. All of those are steroid based. Or all of those are cholesterol based. So we're going to call this one hydrophobic lipophilic. That means that the location of the receptor at the target is going to be different. If you are a hydrophilic hormone, well then you can't cross the cell membrane. So that means that your receptor has to be on the surface. Here's an example of a really nice protein hormone that you've likely heard of. Insulin. Insulin is your very typical protein hormone. An amine hormone, give you an example of an amine hormone in that it is nitrogen based and it is amino acid based primarily. Norepinephrine and epinephrine. Epinephrine in INE, that part tells you it is amine based. Epinephrine is under this. Right? There's a whole bunch of other hormones that are out there, but I want you to know generally what the two categories are and where they would find the receptor. Your steroid hormones, because they're lipophilic, they can get away with not having a receptor on the surface. They actually can get into the cell. So they can cross the cellular membrane at the target, and the receptor happens to be what we call intracellular, which means that it's inside. In fact, that receptor is typically going to be near the nucleus. So typically these steroid hormones, what they do is that they affect the way that we synthesize proteins. They actually go to the genetic material, they go to the DNA, and they actually affect transcription of that DNA. So this is why your steroid hormones, such as testosterone, aldosterone, estrogen, progesterone, cortisol, tend to have very long-term effects. How long-term? We're talking years. Because when you direct gene transcription, that's not an immediate thing. That is a developmental, could be over weeks to months. So these are these tend to have longer effects, those steroid hormones. So those are the two types, okay? There are different ways that we can control the hormones and control their secretion. And there are 3 types of stimuli that are going to cause a hormone to be released. Remember that we don't secrete a hormone unless we absolutely have to. When we think of being within normal range, it's only if we are out of that range that we need to secrete a hormone to get us back into that range. So there are 3 stimuli that are going to cause the release of a hormone. A humoral stimulus means that there is something imbalanced in the blood that is going to cause us to release a hormone. I'll give you an example of that. Calcium levels. Calcium levels in the blood. We have hormones that are going to decrease the calcium, and we have hormones that are going to increase the calcium. We kind of met those hormones earlier. You guys remember the names of the hormones that we met much earlier when we went to bone? There were 2 hormones that were in charge of calcium and calcium levels. Calcitonin, and what was its friend?
I think it was parasympathetic.
Very close, it sounds like it. Para something. Parathyroid hormone. Some of you are already getting prepared for your final exam and are asking questions about the semi-cumulative part. If something shows up more than once, I would pay attention to it. Okay? So those are the 2 that are going to be secreted in response to a humoral type of stimulus. Neural means that a neuron is going to provide the stimulus for the release. So what's an example of this one? Sympathetic nervous system with the adrenal gland. Okay? What is feeding into that adrenal gland? A neuron. Okay? So that neuron is going to cause the adrenal medulla to want to secrete epinephrine. Epinephrine is the hormone, however, there is a neural stimulus that's going to cause that gland to secrete that hormone. Hormonal by another gland. So case in point, and I'm gonna kind of go over this last part and then we're gonna look at our exams Tuesday section, okay? Case in point. Your main gland, right at the base of your brain, it starts with a P. Does anybody remember what it was? What was it? I heard it. The pituitary gland. The pituitary gland is the master gland. The pituitary gland secretes hormones, for example, that is going to directly stimulate the thyroid gland to secrete thyroid hormone. So in order for the thyroid gland to secrete thyroid hormone, it has to respond to a hormone from the pituitary gland. That is what it means to have a hormonal stimulus. One gland secreting a hormone is going to actually stimulate another gland to secrete its hormone, which will in turn cause or can stimulate another gland downstream to secrete its own hormone. So we'll talk a little bit about that, okay? They're secreted in response to these types. of stimuli. They have to circulate in blood, or else by definition they can't be a hormone. And they have to be very specific. That means that the target cell has to have a functioning receptor for that hormone. Specific. Target cells must have a functioning receptor for that hormone. You want to put functioning? That's really important. Here's an example of where you don't have a functioning hormone. Type 2 diabetes. Your hormone is fine. Your functioning receptor is not. Okay? So we'll talk more about that. But a hormone can have different effects on different targets based on the type of receptor that is at those targets. Epinephrine is a great example of that. It has two versions of a receptor, and it does different things based on it. There's a beta version and there's an alpha version of it. But we're not gonna go super deep into that, okay? So, what I wanna leave you with, I know you guys are worried about Tuesday's exam, and I know that. And I know all weekend you are gonna be studying for Tuesday's exam. But do not let this go. Okay? Do not let this go, all right? We gotta catch up on it. So positive and negative feedback, those ideas, that's what we're going to continue with next week, next Thursday, okay? And we're just gonna keep going, all right? If I have to, because of the time that we have, I may have to post some video lectures of certain ones to ensure that we get through all 11 systems in this class. So what you guys have to do, our goal is we need to go through all 11 systems in total for 209. Okay? So if I need to, I will let you guys know. But for now, don't leave this in the dust, and good luck on Tuesday. All right? And then Tuesday section, I have your exams here.